Number 44. Isotopes such like 26 aluminum, which has a half-life of 7.2 times 10 to the 5 years, are believed to have been present in our solar system as it formed, but have since decayed and are now called extinct nuclides. Cool. So letter A, it says aluminum-26 decays by positron emission or electron capture. Write the equations for these two nuclear transformations. Okie dokie. All right, so let's do letter A. Now, in this case, all we have to do is just write the two equations in which aluminum is going to decay by positron emission or by an electron capture. So since we're dealing with nuclide notation, right, and nuclear reactions, we usually just write these with those three boxes, right, which are these right here. So what we're going to do is we're going to do one of them with the aluminum-26 positron, and then we're going to do the other one by the electron capture. So let's start off with that aluminum, so Al. Now they told us that the mass number is a 26, so I'm going to put that in the upper corner, right? The mass number, the number that they give you, because that could change, goes in the upper corner, but the atomic number always stays the same. And we got to look on the periodic table to know what the atomic number for aluminum is, which is always going to be 13. Now let's do positron emission first. Now whenever you're emitting a particle, you are always going to be releasing it into the atmosphere. So an emission is always going to be on your product side. So I know that this aluminum is going to now yield into that positron particle, right? It's going to give off the positron particle. So let's write that one down. And usually with positrons, positron, which is the beta positive, we could say beta. But now a positron is the opposite of an electron. They both have a mass number of 0 because they're not included in the nucleus. But a positron, since it's positive, it's going to be a +1. The electron is going to be the -1. But now we just need to make sure that this equation is balanced, right? Which means that I definitely need another nuclide that the aluminum actually turns into. So in this case, right, we have 26. We can yield this to be an equal sign, right? Use this yield as an equal sign. So 26 equals 0 plus what? Yeah, this has got to be a 26 on the top. And then 13 equals 1 plus what? So 1 plus what will get me 13? Yeah, you got a 12. And now the number, the atomic number, is always going to be what the element is. So in this case, we're going one number down, which is going to be magnesium. So this would be our first equation. Now let's do the same thing for the electron capture. Now, if you're capturing something, you're, taking it in, right? You're holding it in. Capturing means that that particle is now going to be on the reactant side. So I'm going to take my subatomic, well, not my subatomic, but my nuclide notation. We're going to start off with the aluminum again. So Al, 26 on the top, 13 on the bottom. And now since I'm capturing an electron, it's going to be plus that electron. Now in this case, we can say that it's a beta, right? Or you could say it's an E. So we'll say beta electron is a beta. And it's the opposite of a positron, so it would be 0, but then it would be a -1. And this will now yield into your new nuclide. So you still do the same thing with the tops and the bottoms, right? So 26 plus 0 is 26. 13 plus a -1 is still that 12. So this would still be magnesium because it's the same as before. Always look for that atomic number. And here we have our two equations. So part A is done. So maybe what I'll do is maybe we'll draw a line here. And now we're going to go, and maybe actually what we can do is, maybe we'll start up top here for letter B. Now letter B says, The Earth was formed about 4.7 times 10 to the 9th. So that's 4.7 billion years ago. How old was the Earth when 99.999999% of the aluminum-26 that was originally present had decayed? Okay. So, long story short, they're asking for how old was that Earth. Okay. So, how old, right? If I ask how old you are, you would tell me some number years old, right? So whether you're 18, 19, 20, 56, I don't care, right? 81, right? Everybody's welcome to watch these videos. But it's usually going to be a year, right? I don't think anybody who's 3 months old or, 3 days old, 3 months old, 3 hours old is going to be watching this. But anything's possible. But anyway, how old was the Earth? It's going to be in unit of years. So if we're talking about a unit of years, we are talking about a unit of time. So secretly, we're searching for a time value. And this is a general time value. If you're using your formulas for radioactive decay, just always know that radioactive decay abides always by first order kinetics. And you've learned these formulas if you've already done your kinetics chapter. Usually with this chapter, they like to give you, new formulas to memorize, but they're the same as your first order kinetics. So why can't you use those? I just like using those, right? So we're going to try to solve for that unit of time. Not necessarily a half-life, because this is just a random time value. So I know that I have to use this formula because I want to solve for that t value. But now, if I'm going to try to solve for that formula, I need to know a k value. And the k value is always the rate constant. But nowhere in this formula did they tell me a rate constant value. But they gave us a half-life, which is now the t half. So what we can do is we can use this formula first, right, to solve for that k value to use for the one that I really want. Now, the half-life for aluminum, they did tell me, was 7.2 times 10 to the 5th years. So we're going to use that and solve for x. So let's go for it. 7.2 times 10 to the 5th equals, we got 0.693 on the top. That's a standard value for this equation, divided by k. You can cross multiply and then divide. Woo! Wee. 7.2 times 10 to the 5th k equals 0.693. We want to solve for the k value. So let's divide on both sides by 7.2 times 10 to the 5th. This will cancel out. And let's find out what that k value is. So 0.693 divided by 7.2 times 10 to the 5th, 9.625 times 10 to the negative 7th. And since we were in units of years, this is going to be per year, so year to the minus 1. Now, let's go for this formula, right? Keep in mind, we wanted to solve for that rate constant, the 9.625 times 10 to the negative 7th, because we want to solve for that t value. But now, if this is our variable that we're searching for, we should know these two units of quantity. Now, the great thing about this formula is that you could put in units of grams, molarity, mole, whatever. You could use fractions and percents. Now, they did start us off with the percent, so I know that I'm in that unit. Now, how old was the Earth when 0.9999 of the aluminum has decayed? So, let's start it off, right? This A0, 0 means that 0 time has gone by, so this is your initial percentage. And if nothing has decayed, how much percentage of aluminum did you have? Yeah, you always start off with 100%. Now, the key to this formula is that the other A value is what you have remaining. So this is your amount that's remaining. Now we have to read this very carefully because they said that 99.999999% of the aluminum had decayed. That means that it's gone, and it is never to be seen again. That's not how much is remaining. That's how much is gone. So, if we want to find out how much is remaining, we're going to take the total, 100, minus how much decayed, 99 point. How many zeros are here? 2, 4, 6, 9, 9, 9, 9, 9, 9. I'm just going to do this in the calculator just so that I have that number ready to go. So 100 minus 99.1, 2, 3, 4, 5, 6, 9s. 1, 2, 3, 4, 5, 6, 9s. And there we go. 1 times 10 to the negative 6th percent is remaining. So now, here we go. We're going to use this formula. We're going to plug it all in and solve for the time. So ln of equals negative, maybe we need a little bit more, plus ln of, okay. So we got 1 times 10 to the negative 6th percent that's remaining. This ln is going to be the initial, which was 100. We're going to solve for that time, and then we have the 9.625 times 10 to the negative 7th. Okay. So now let's do these two values first. Hopefully Calci can do it, because if Calci can't do it, ooh, that's not going to be good. So we'll do ln of this value. Okay, so negative 13.8155 equals negative 9.625 times 10 to the negative 7th times the time value plus the ln of 100. We get 4.605. We want to solve for t, so let's get rid of that 4.605 minus 4.605. 4.605, that goes bye-bye. Oh boy, we're running out of room here. But let's see. I'm going to take the full numbers here, so this minus this value, I get, oh boy. Can we, no. What can I do? Can I do some magic? Can I maybe? Okay, that might save us. Let's see. Negative 18.42 equals negative 9.625 times 10 to the negative 7th, and that's times by t. So we want to solve for t. So you know that we have to, oh boy, divide by the value. 9.625 times 10 to the negative 7th. 9.625 times 10 to the negative 7th. This cancels out. Woo-hoo. This divided by the negative value, because I want to get rid of that negative. And I think I have the number in here. Let's just go up. There we go. And it's a negative. So hold on. Negative. Let's see. Am I gonna? Oh boy. Let's just delete all these other numbers. Just make sure that we got it in correctly. The negative 18 and then divided by the negative. Yep, that looks good. Okay, there we go. So t equals 1.9. How many decimals is this? 1, 2, 3, 4, 5, 6, 7. 1.9 times 10 to the 7th years. So this basically means that once the solar system was made, right? When you had all the aluminum, you had 100% of the aluminum. How old was the Earth when basically this amount of aluminum decayed? It was only 1.7 times 10 to the 7th years old. It is now 4.7 times 10 to the 9th years. So there is no aluminum that basically was present in the solar system that we see now because it's all gone. And that's basically the answer here. So we answered A, we answered B, and we are done for this question. What'd you think? Thank you so much for watching the video and, doing it along with me. I hope this helps you out. Let me know in the comments. Subscribe to the channel if you haven't already. Just gets the word out there in the YouTube universe that this educational channel exists. Thank you for all your kind comments in the comment section. I try to get back to you as much as I can in my free time. And if you want to help the channel out a little bit more, there's always memberships. We just opened it up for the new school year. So you could check that out. There's 4 tiers, different perks. So maybe one will suit your fancy. And I hope you're having a great day. Keep studying hard, and I'll talk to you soon. Okay, bye-bye.